plus a n y of n minus y of n minus capital N plus b0 x of n plus b1 x of n minus 1 s plus bm x of n minus n. Right? So this is a very simple system that I can compute. And I studied very general difference equations. And you can see that I can really easily implement them in mathematics, right? Or any circuit. So the key question we need to understand is, how should I find this number? How should I find this number? All of this number, by playing around with this number, I will have a difference equations, giving me a different systems, right? And then I can use that to, and I leave you as exercise. You can show that this is one class of LTI system. Right? So design LTI system is designing those numbers. Okay. Is it still clear? All right. So here, let me ask you a question. If I just give you this, take it as a computer, can you go ahead and implement this? Or do we miss anything else? What else do I need to specify apart from this equation? So this equation, I can run them, for n, any n, right? N is the integer, so I can just keep running that. So anything else I need to specify? I need some initial condition, right? So maybe at first start from this n location, right? I assume I have something, and then from there I can just move on. All right. So this one plus with the initial condition. Some initial conditions, node maybe equal IC, and that maybe we can give us a value of y of 0, y of n. So you can see that y of n minus 1. So having this n sample, I'm ready to go, right? I can now compute every sample. Yeah, go on. Oh, okay. So where the threshold? About here? Okay. All right. So let me put here. So this one here, what you need to have is you need to have the initial condition with required to have on the value of y and go from 0 to n minus 1. Okay. You need to have initial condition so that you can really kick off the system and it keep going. It can run. All right. So that is a simple thing. And let me say right away that all the LTI systems, all the filter that we can implement, or it's being used now, are just of those forms. Okay, so this is a complete characterization of the system that's being used nowadays. Okay, or we will make the study because it's so easy to implement. Okay, so we will going to restrict ourselves to this class of systems, even though there are other systems. Because you see, if I'm going to give you, here I give you a simple example here. If I take this one here and I can write this. I can write this equal to summation of h of k x of n minus k. And k go from minus infinity to plus infinity. So that's the convolution operation, right? I can show you that and say, okay, go on, implement it. But right away you can come back and tell me, hey, but now I have this infinite sum. How can I compute it on a computer? right? I cannot compute them in a computer. So I only can compute them with a finite number of terms. So if I only can compute with a finite number of terms, that is when I'm going to just ignore this part. Right? It's a linear combination of the input. But there's some clever class of system, it's called recursive, because if I allow those, I can allow this thing to be infinite sum, conceptually, but not actually. Right? I'm not going to compute them, but I'm going to compute them in this form. Okay, is that clear? Let me repeat again. This convolution operation is only good for mathematical analysis. Actual implementation, you need either a finite number of terms. That means you only have this. Or, if you want to have an infinite number of terms, you can't choose any infinite number of terms. You have to choose something satisfy this form. Okay? So that would be two classes of filters. And by the way, if you know them, I will talk more, but it is the one that has a finite number of terms is called finite impulse response. Right? You call it, this is impulse response. So maybe we say here, the filtering here, oh, I shouldn't write here. We can write up here. The two terms I would like to start. The FIR is finite. This impulse response here, impulse response, where this h of k here, and k only go from, well, h of k, well, maybe it's easy to draw now. H of k is equal to 0 outside some interval. It's only non-zero in a finite interval, finite impulse response. And you can see the importance of that, because having that means I can compute them using this convolution. Right? Otherwise, I cannot do this convolution. And this thing comes in a little bit helping us, it allows to design some kind of infinite impulse response, but not every infinite impulse response. Okay? So that one. Now, to understand the filter, one thing that digital signal processor use very effectively, and we need to master that concept, is the so-called Z transform. So who here have seen the Z transform before? The Z transform. Or Z transform. Oh, there's more from Z transform. Okay, so I call them Z transform then. No, in the US we call Z transform, right? Okay, so let's practice that. So the Z transform, okay, so a lot of you are already familiar with that Z transform. It defined, let's say I have a signal Hn, and n is an integer, then I simply computed the Z transform it by writing as Z is equal to summation of Hn, Z to minus n, and go from minus infinity to plus infinity. Okay, oh, there's one thing yesterday someone told me. We're going to use, whenever I don't write anything, the limit here, I assume that it goes from minus infinity to plus infinity. When I write integral, I don't put the limit, I assume from minus infinity to plus infinity. It's not the indefinite integral. Okay, so that's the definition of the Z transform. And maybe we should take some example.